In the next few math talks, we're going to be examining applications of quadratics, specifically what we call optimization problems. And those are problems where you are being asked to find, let's say, the largest area or smallest cost for a manufacturing process, or the highest revenue you can generate from a particular business. Anything that involves a high or a low is what we call an optimization problem. And they are particularly suited to quadratics because quadratics have that characteristic vertex, that low point or high point, depending on which way they are oriented. Now, we spent a few previous videos focused on finding the coordinates of that high point and low point, and that's what these questions will be about. The challenge in the questions will be centered around actually finding the equation of the quadratic relation. So we're going to begin with this problem. At $52 for an oil change, a garage services 60 vehicles per week. For each $2 price increase, the garage services 5 fewer vehicles. What price will maximize the revenue for the garage owner? Well, as I said, the challenge is building that quadratic relation to start with. So I will begin like I do with any of these problems with some sort of let statement or diagram to introduce variables to help us in our problem. I say let X represent the number of $2 price increases, and I do that because the problem is sort of stated that way. We talk about for each $2 price increase, the garage services 5 fewer vehicles. So it makes sense to describe things in terms of $2 price increases. And of course, the thing that we're trying to optimize is our revenue. So I'll let R represent the total revenue. To help build a relationship between R and X, I'm going to give you just a table of values here, where we're going to look at the price increases, we're going to look at the price for the oil change after the price increase, and then we're going to look at the number of units or the number of vehicles that we will be servicing at this garage. So if I have no price increases, in other words, if I make no change in the current price, it's $52, and the number of vehicles that get serviced are 60. However, if I make one price increase, in other words, I up the price by $2, it becomes $54, and the number of vehicles drops to 55. For 2, my price is now fully up to $56, and the number of vehicles serviced would fall to 50. What I'm trying to establish is what happens if I just make the price increases X? Well, I think when you look at the pattern, every time I increase by 1 unit, my price goes up by $2. So starting from $52, I would have a price of $52 plus 2 times whatever that X is, whatever the number of price increases are. And similarly, the units drop by 5 for each price increase I make. So starting at 60, they would drop by 5 times X. So now to calculate revenue, revenue is just unit price times units sold. So if I take my 52 plus 2X multiplied by my 60 minus 5X, I will get my revenue. Now, the next step in my process, as one of my ways to find a vertex, was to find X intercepts. So that's what I'm going to do next. In this problem, we're perfectly set up to do this. The revenue is already in factored form. So I look at each factor individually. So I'd say 52 plus 2X equals 0 for one X intercept. That would give me X equals negative 26. And then the second X intercept would come from the 60 minus 5X equaling 0, or X equals 12. And we learned this in an earlier video. Now, graphically, it's going to look something like this, where I have an x-intercept of negative 26 and 0, a second x-intercept at 12, 0, and in order to find the vertex, I recognize that vertex sits on the axis of symmetry that splits right down the middle of that parabola. And that axis of symmetry marks a location where points are equidistant from each other. So in other words, we know that the two x-intercepts lie in equal distance either side of that axis of symmetry. So in order to get the x-coordinate of that axis of symmetry, we simply average the two x-coordinates of the x-intercepts. And so we say to get the x-coordinate of the vertex, we take the negative 26 from the first x-intercept and the positive 12 from the second x-intercept, add them and divide by 2. We take the average, and that's negative 7. To get the y-coordinate of that vertex, or the revenue coordinate, as we would call it in this case, our revenue coordinate would be 52 plus 2 times that negative 7 times 60 minus 5 times that negative 7. So we've just inserted the x-coordinate of the vertex, and we get 3,610. And now we need to make a concluding statement. And what's interesting in this problem, something that we didn't even consider in the opening statement, was that it might make sense not to increase the price charged for an oil change, but to actually decrease it. And we see that at the vertex, we get the highest value for revenue when X is a negative number. In other words, we have price decreases. So we're going to decrease that price 7 times. We're taking it down 7 times, or 7 $2 increments. Well, for my concluding statement, I would say the price of an oil change should be lowered to $38. That's the $52 plus 2 times negative 7. And that will increase the number of oil changes to 95 per week, and that will maximize the revenue at $3,610. And that's all there is to that problem.